Hello. On my last video, we gave our definitions for sum, difference, product, and quotient. And the definitions are actually twofold, right? We're talking about a sum versus the sum of particular numbers. So make sure you have all of those definitions in your notes. But I want to look in this video at a few sort of classic examples that we tend not to think about at the same time. I think that's a shame. So let's start with a number. Let's say 528. And I could talk about the sum or the product that leads me to 528. Now, the classic way of thinking about this for the sum is expanded form, right? Where I look at 528 is 500 plus 20 plus 8, right? The way our numeral system is based is off of powers of 10. So you look at 8, 10 to the 0, 8 ones. 20, that's 2 tens, 2 times 10 to the power of 1. And 500, that's 5 hundreds, 5 times 10 to the power of 2. We can just show that with 2 zeros there. Right, so even though I'm showing multiplication to indicate what those units are, the format of expanded form is as a sum. Right? I'm thinking of the sum of 528. This is the most obvious one. But if I'm doing something like long division, 500 plus 20 plus 8 doesn't necessarily help me depending on what I'm dividing by. If I want to do 528 divided by 5, well, that works great here. 5 doesn't go into 2 evenly. If I turn it into a 20, I could do that. 5 doesn't go into 8. That's not so nice. Maybe 528 divided by 2. I could take half of 500, I hope fairly easily, right? 250. But I'm not going to do that a digit at a time. If I'm doing 528 divided by 2, I can't just say that's an even number of hundreds to say how many times 2 is going to go into 500. Right? So if I'm doing long division, this also isn't the best sum for that. Now, there are actually way more possible options here than it's ever going to be useful to list. So let's switch to a smaller number to look at that. Let's think of, say, 12. Right? What are the sums of 12? Well, the classic and expanded form, 1 10 and 2 ones. But there are other sums we can get to give us 12. I could say 11 plus 1. I could say 12 plus 0. I could go the other way, go 9 plus 3, 8 plus 4, and so on. A sum doesn't have to just be 2 numbers, though, right? Here I saw a sum that had 3 numbers. So to add up to 12, that could be 1 plus 1 plus 1 plus 1 plus 1 plus 1, 12 times, right? Not terribly interesting. I could replace one of those with a 2. So it's 2, then 3, then 4, then 5. Instead of dot, 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 let's say 5 plus 7 is 12. So 7, 8, 9, 10, 11, 12. There's a sum of 12. Right? Really, for any digit, any multi-digit number, even for one-digit numbers, the number of sums available is enough to not be worth considering. Right? The only sum we usually care about is expanded form, where I'm looking at sums of ones, tens, and hundreds we have here. Or the particular sum that's useful for long division. The long division process gives that to me without me having to come up with it first. Right? I don't have to see, well, 528 would be 400 plus 120 plus 8. I just say 4 goes into 2, sorry, 2 goes into 5 twice. 2 times 2 is 4, so there's my 400. There's my 12 now in the tens place, so that's 120. 2 goes into 12 6 times. And then I bring down the 8, right? So 400 plus 120 plus 8 is 528. And 2 times 4. Finish that up, right? So 2 times 200 is 400. 2 times 60 is 120. 2 times 4 is 8. So splitting it up that way gives me a nice way to multiply to get the original dividend. But I don't have to think about it that way. I'm just using the regular single digit process here because of a single digit divisor. I'm not really thinking of this as a sum. So sums as a type of way of expressing a number are pretty boring. What is not boring is products. So if I start over with 528, I can ask myself, well, what could I multiply to get that number? Or maybe there are several things I could multiply together and get 528. It's not nearly as obvious as the sum. It's also a much smaller set of choices, right? We could have spent the rest of the day, probably the rest of the week, listing all of the different possibilities of what numbers I could add up to get to 528. There are thousands of them. Even for 12, I haven't done the calculation, but it's in the 20s, I'm guessing. Yeah, somewhere around there. So for products, the number of products that give me 12 is much smaller, so long as I limit myself to just whole numbers, right? So try to think, what is one pair of numbers you can multiply to get 12? Classic one that most people come up with first is 3 times 4, right? 3 times 4 is equal to 12, so that is a product that's equal to 12, a product expression, two numbers whose product is 12. There's another one here. Let's say 3 is a little bit smaller. To compensate for that one getting smaller, the other one has to get bigger. So 2 times 6 is 12. I could go even smaller than 2, but that means this side has to get even bigger. Right? If we're thinking of arrangements of blocks here, if I have 4 in a row, another 4 in a row, another 4 in a row, there's my area, length times width. 3 times 4 is 12. If I want to rearrange this by cutting out one of those rows, well, those 4 have to go into one of those rows. So there's 1, 2, 3, 4, right? There's my 2 times 6. If I want to rearrange those so that I only have one row, those 6 have to get moved up here. And there's 6 plus 6, there's 12 times 1, 12 by 1 gets me 12. Right? So 3 different arrangements to get 12. Those are the only choices. Right? I can rotate 90 degrees, and instead of 1 by 12, I could go 12 by 1. Or 6 by 2. Just drawing circles because it's a lot faster than squares. Or 3 by 4. But it's really the same pairs, just rotated vertically versus horizontally, right? If I do introduce negative signs, even that doesn't get me that much farther, because if I put in a -3, in order for the product to be a positive 12, then I need a second negative there, -4. That goes down, -2, -6, -1, -12, right? So 1, 2, 3, 4, 5, 6 pairs. But didn't you just say Professor Newman, that you don't always have to have a pair. You could have 3 or 4 or more of those. Well, you could. So how can I possibly come up with more options based on what I have here? Well, I look at what I have and see how much further I can break it down, right? If I want to split this product of 2 numbers into a product of 3 numbers, one of these has to get split. 3 is what we call a prime number, right? The only product I can get 3, if I wanted to write 3 as a product, my only choice is 1 times 3, or bring in negatives, -1 times -1, -1 times -3, okay? For now, we're going to ignore the negatives that just kind of clog things up here. I hope you get the idea that the product of 2 negatives is a positive, and we'll leave it at that. We're going to focus on just the positive factors. All right, so 3, I don't really have a choice. 3 is just 3, but 4 is 2 times 2. So from 12, I could split that up as 3 times 4, leave the 3 alone, and split up the 4 as 2 times 2. And so there's a product with 3 factors in it, right? Factors are the inputs for multiplication. A product of 3 factors, and the product of those 3 factors is 12, right? So again, I'm using the word product to describe the expression, and the word product to describe the output value, the single value of that expression of 12. Well, that's the process that we call factoring. If I use the word factor as a verb, I'll write that out here. Let's put in a verb explicitly. We already have a noun definition of factor, right? The factor is an input value to the operation of multiplication. That's what we've been using for weeks now. But if I talk about factor as a verb, I mean rewrite a given number or expression, we can factor entire expressions as well, as a product of whole numbers. We'll talk about one in just a moment. Or expressions, right? So if I factor an expression, that's going to be rewritten as a product of expressions. For now, we're just factoring numbers, and we're writing those numbers as a product of whole numbers, right? So the key word here is we're still getting a product. And so that actually leads us to another noun definition, a slightly different way of thinking about factor. My underline's in the wrong place, that's okay. Remember, because product is not just the particular product of 3 times 4, but a product can also be thought of as the whole expression. So a factor can also be thought of slightly differently. A factor is a whole number that can be multiplied by another whole number to result in a given number. All right, so let's make all this a little bit smaller. All right, now it all fits on the page. This round, there we go, underlining word product there. All right, so let's apply this to the example we were just looking at, which is 12, right? If I tell you to factor 12, that's the command, that's the imperative verb here. Factor 12, what are you supposed to do? You're supposed to rewrite 12 not just as the sum of 10 and 2 without the plus sign, but as a product. You can write it as a product or as this product or as this product. Now here's where I mean usually excluding 1. When we say a number cannot be factored, that's like saying factor 3. Well, there's nothing to do there. The only option is 3 times 1. It's boring. Right? If I say factor 17, okay, what numbers can I multiply to get 17? It's just 1 and 17, right? So if a number is prime, it has exactly 2 factors, 1 and itself. And we usually just say that's unfactorable. This factor pair is not interesting. So we ignore 12 times 1, usually. There are times when we'll need to recognize that 12 times 1 works, or that 3 times 1 does work for 3. But if we're trying to do the factoring, we're trying to get new numbers, not the original number and 1. Okay? So rewrite a given number as a product of whole numbers or expressions. So we'll get to factoring expressions in a little bit. All right, now, it doesn't say a product of pairs of whole numbers. Right? It's not just these two, it is also this one. So the question is, how do we get to this one? And how do we differentiate it from either of these? Right? And that process is a way of coming up with all of the factors of 12. Right? So a quick note before we move off of the screen. This word factor means this definition. Right? Is to write the product. Right? Rewrite the number as a product. So this is one of my answers, and these are some other possible answers to that question. That's a very different direction than asking you to list the factors. All of these numbers, 1 and 12 and 6 and 2 and 3 and 4, they already have 3 and I already have 2. All of these are factors of 12, right? So let's see that definition. I didn't actually say it out loud before. A whole number that can be multiplied by another whole number to result in a given number. So what number were we given? We were given 12. So if I ask you to list the factors of 12, I'm going to ask you to list what could possibly go in to either of those blanks to get 12, so long as both of them are whole numbers. Because once you bring in fractions, then any number can be a factor of any other number. Okay? So what could I multiply here? Could I put in 1 times something? Yeah, 1 times 12 is 12. So 1 is a factor of 12. Can I put in 2 times something? Yes, 2 times 6 is 12. Can I put in 3 times something? Yes, 3 times 4 is 12. Can I put in 4? Yes, 4 times 3 is 12. Can I put in 5? No, right? Here's our first whole number that is not a factor of 12. I can't multiply 5 by another whole number and hit 12, right? 5, 10, 15, 20, 25. I'm never going to land on 12. So 5 is out. Can I put in 6? That's getting too busy here. Okay, 6 times something. Yeah, 6 times 2 is 12. Can I put in 7? No, 7, 14, 21, that's not going to work. 8. Okay, well, 8's promising, right? If 4 works, maybe 8 works. 8 times 1 is 8. 8 times 2 is 16. I'm already past 12, right? 8, 16, 24. I'm going beyond 12. I'm never going to land at 12. So 7 doesn't work. 8 doesn't work. 9, 10, 11. None of those can I multiply by a whole number and get 12. But then 12 does work. 12 times 1 is 12. So if I asked you to list the factors, you're listing out all the numbers that could go here, right? That's different than asking you to factor and get that product. Right? They're certainly related, but they're different types of questions, different answers here. All right, so how do we get these numbers? And how are we going to do this for 528? So two factor, my method that I almost always use is called a factor tree. And there's slightly different ways of writing this, but basically you start with your number and you come up with whatever pair pops into your head first. So if most of us are saying 3 times 4, I know 3 times 4 is 12, that works. There's a product that gives me 12. Well, then I want to see, can I break 3 down any farther? No, it's a prime number, but 4 can be broken down. So the fact that I can go down another level means I need to bring 3 down to that same level. And okay, well, what can I multiply to get 4? Well, 2 times 2 is 4. And now 2 is also a prime number, just like 3, so I'm done. I didn't have to start with 3 and 4. I could have started with 1 and 12. Right? That's another pair of numbers that multiply to get 12. But I haven't really made any progress, right? That's why we say this numbers that can only be broken down this way really can't be factored, right? I could just go on forever. Bring down my ones here. I have too many ones to even keep track of, right? This is not terribly interesting. 12 times 1 a bunch of times. No one cares about that. So we're never going to use 1 and the number in our factor tree. But we do have another choice here. Instead of 3 times 4, I could have used 6 times 2. And 6 is 2 times 3. But 2 is just 2 times 1. So we'll just leave that as 2. Right? Notice, if you're comfortable with the commutative and associative properties of multiplication, that these two expressions are identical. And to help us see that they're identical, especially when we have a lot more factors than just these 3, we like to put them in increasing order. So let me write that in words here. When writing out factorization, we'll talk about what a prime factorization is in just a moment. But going in increasing order, we can all look at the same list at the same time, right? It's like looking at a class roster. If I have one list that's alphabetical by first name and another list that's alphabetical by last name, another list that's listing people based on their last test score, it's going to be really hard to find the same name in all 3 lists, or to make sure that those 3 lists list the exact same names, right? But if it's always alphabetical, then it's very quick and easy to see that these lists are all identical, right? So of these 3 numbers, which is the smallest? 2 is the smallest. So I'm going to write 2 first. Then the next smallest is also 2. Those are ugly check marks. Then the next smallest is 3. Going this way, the smallest is 2. Next smallest is 2. And then the next smallest is 3. So that would be the fully factored version of 12. And fully factored is another way to say prime factorization. Right? So prime factorization is a number expressed as the product of prime numbers. And once you've got all prime numbers, there's nothing left to do on my factor tree. That's as fully factored as it can be. If I think of splitting it up, whether it's 2 or 3 or 5, that's the most individual numbers I can multiply and get that starting number. Right? So prime factorization, a number expressed as a product of prime numbers. So if we're using it as a verb, that's to factor a number into its product of primes. If we're using it as a noun, that is the number expressed as a product of prime numbers. Right? So if I say find the prime factorization, now this isn't really a verb, I would use the word find. If I say find the prime factorization of 12, or give me the prime factorization of 12, this is what we're looking for. 12 split down, broken down as far as it can go. All right, so what about this 528? Right? How can I multiply certain smaller numbers and get to 520? That's a big number, and it's not a number I'm terribly familiar with. Let's write it down and kind of think about it for a minute here. 528. Well, it ends with an 8, so I think that's telling me some information, but it's not picking up any of my times tables that I've memorized as an obvious starting point here. Right? Now, an easier number would be something like 520. Right? Also, a number too big for your memorized times tables, but there's some detail about 520 that makes it much more convenient than 528. You guessed it, that 0. Right? If it ends in a 0, that means I'm just counting by tens. Right? If I look at this in expanded form, I could say 5 hundreds and 2 tens and no ones, right? So 5 hundreds, that's 50 tens. 2 tens, that's 2 tens, right? I'm counting tens. I have 50 plus 2, I have 52 tens. Anytime your number ends in a 0, you're just counting by tens. So we can write that down. We'll say divisibility equal for 10. Given numbers ones digit 0, right? Given number apostrophe possessive, right? The given number's ones digit is a 0. I don't have any ones. I'm just counting however much I have in front of the 0. I have that many tens. If I have 52,000, that's super easy to factor as well, at least to get started. That's literally 52 thousands. Right? Now, 1,000 is not a prime number, so I'm going to have to keep on going here. But at least that first step gets me really almost to the end, because now I just have a 2-digit number that I do recognize from my times tables. And I'll go from there. 1,000, we'll look at factoring multiples of 10 shortly. Right, so let's take this only a little bit at a time here. So 520, I have 52 and I have 10. Well, 52 does not end in a 0. That's not just counting tens, but it does have a 2. If I think of 52 in expanded form, that's 50 plus 2. It's a multiple of 10, and 10 can be factored. What are the factors of 10? 10 is 2 times 5. So 50, that's 5 tens. So 5, 2, and 5s, plus another 2. Right? I have 2 as a factor here and 2 as a factor there. I can use the distributive property to factor in reverse. We're kind of getting ahead of ourselves here. Basically, put my time symbol in. Basically, we're saying any 2-digit number that ends with an even number, an even ones digit, is going to be even, right? And it's because every 2-digit number that's a multiple of 10 is a multiple of 2. Anything that's a multiple of a number is a multiple of its factors. So if I have something where 10 is a factor, then 2 and 5 are also automatically factors. 10 is not a factor of 52, but 2 is a factor of 10, so 2 is a factor of 50, and 2 is also a factor of 2. So that means 2 is a factor of the whole thing. So I can write 52 as 2 times something. Question is 2 times what? So 52 divided by 2. With factoring, we do a lot of long division to find that second number. Our divisibility rules give us a yes or no, whether 2 will go in, or 3, or 5, or 10, but it doesn't necessarily tell me what that other factor is going to be. I have to do the long division to find the other factor. So 2 times 2 is 4. Bring down this 2. 2 times 6 is 12. And as I knew ahead of time, there would be no remainder. So I have 2 times 26. So 2 is a prime number. 5 is a prime number. Put in all of my multiplication signs here. 26, 20 is a multiple of 10, which means it's a multiple of 2 and 5. And 6 is still even. 6 is a multiple of 2. So I know 2 will go into 26 evenly. 26 is 2 times 13. So I get 2 times 2 times 13 times 2 times 5. Now, if you're like me and you're familiar with weeks of the year or with cards in a standard deck of cards, you're used to 52 being 4 times 13. Well, here's my 4, and there's my 13. And kind of previewing one of the uses of getting the prime factorization is to then identify all of the other factors that I didn't necessarily use in my factor tree. Right? So there are a lot more factors of 520 than just the numbers already written here. Any product combination of any of these numbers will also give us 520. Right, so the prime factorization of 520, I'd say 520 equals 2 times 2 times next smallest is this other 2, then the next smallest is 5, then 13. And if you want to get fancy, because I have a whole bunch of 2's here, I can use an exponent. 2 to the 3rd power times 5 times 13. Right. I tend to use the dot there just, otherwise it would look like 513, right? If we don't have exponents on all of the numbers, just use the dot. So both of these are prime factorizations of 520, but ask about 528. So I already used the divisibility rule for 2. Let's write that, and then we'll move on to 528. So divisibility rule for 10. Let's just copy this. Because 2 is a factor of 10, I only need to look at the ones digit. The ones digit has to be a multiple of 2, a single digit multiple of 2. So either 0 or 2 or 4 or 6 or 8. What's the other factor of 10? Good. I hope you said 5. So 5, we're also looking at the ones digit, and the ones digit could either be a 0 or a single digit multiple of 5. There's only one of those, right? So for 10, the ones digit's a 0, that's super easy. If the ones digit is not a 0, it's either a multiple of 2, a single digit multiple of 2, or 5, a single digit multiple of 5. So finally, 528. Let's look at that here. 528. 28, all right, it doesn't end in a 0, but it ends with an 8, and we just saw from our divisibility rules that that means 2 is a factor. So let's go off to the side here. 528 divided by 2. 2 goes into 5 a few times. 2 times 2 is 4. Bring down the 2. 2 goes into 12 6 times. Because 2 times 6 is 12. I get no remainder, but I'm not done because there's still a digit here, right? 2 times 260 would be 520. That's what we saw over here, right? 2 times all of this, well, that's 10 times 26. 2 times 260 is 520. But I don't want 520, I want 528. So I need 2 times 264, because 2 times 4 gives me 8, and I have remainder 0. All right, so 2 times 264. All right, well, 4, that's still even. So let's take 264, do that long division. And this one's super easy because each digit here is even. So 2 goes into 2 1 time, remainder 0, 2 goes into 6 3 times, remainder 0, 2 goes into 4 times, 2 goes into 4 2 times. Right? If we double 132, we get 264. So this is 2 times 132. Right, still even. So 2 is not the only number that ever works, but I've got a whole bunch of 2s here that do work. So the long division is kind of annoying to have to do so much long division, but I know I can keep going. So 2 goes into 1, it doesn't. 2 goes into 13, well, 2 times 6 is 12. Bring down the 2, 2 goes into 12 6 times. No remainder, so I've got 66. So I've got 2, 2, 2, and now finally I have a small enough number that my other times tables are kind of kicking in, right? Now, is 66 an even number? Good. So I could take another 2 times something, do the long division there. But I could also recognize 66 is 6 times 11, right? There isn't really a divisibility rule that works for any size number for 11, but I think by this point in your math career, you recognize 11, 22, 33, 44, 55, 66. For 2-digit numbers, if it's just repeated, that works. For 3-digit numbers, the trick for some of them, and this breaks down at some point, is the sum of the outside numbers gives you the internal numbers. So if you have something like 12 times 11, right? 1 times 12 is 12. Then we move over to the tens place, but we're still doing 1 times 12, right? So it's the 1 and the 2 together being added up in the middle here to get 3, and the 1 on the outside and the 2 on the other side, right? So 132, I'll just look at the 132 part. I could factor 132 2 times 66, or I could factor 132 2 times 6 together first. That's 12 times 11 is 132, right? I didn't recognize that right away. I jumped to the long division. That works. 12 times 11 is not more correct at this stage than 2 times 66. Just like 6 times 11 is not more correct at this stage than 2 times 33, if I'd split it up as 2 times something, right? Because 6 is not a prime number, we can split that 6 up one more time, 2 times 3, and then the 11 and all of these first 3 2s are still there. And just sort of by coincidence, because I had a bunch of 2s, which is the smallest possible factor other than 1, it's already in order. So I'm going to say that's 1, 2, 3, 4 2s, and a single 3. I could put 3 to the first power, but most of the time, our exponent's going to be 1 anyways, right? 3 to the first power is just 3, so I'll just write the 3. So if I multiplied all of this up, I would get 528. So that's how we factor our numbers. Now, we're not always going to be in such a convenient place that we can just factor a bunch of 2s until we get a convenient small number that we're familiar with, whether that's 66 or going further to 33, recognizing that as 3 times 11. So it'd be nice if we would have more divisibility rules than just 2 and 5 and 10 and have to guess our long division for everything else. Fortunately, there are a couple more that I'll put up here. And they're a little bit more complicated, actually quite a bit more complicated, but still easy enough that they're useful. So the divisibility rule for 3 states that the sum of the given numbers digits, I remembered my apostrophe this time. The sum of the given numbers digits is a multiple of 3. And that also works for 9 for the exact same reason. And now is as good a time as any for a definition for a word I've used several times already, and that is this word multiple. A multiple is a number that can be achieved by multiplying a given number by some other whole number. So it's kind of the reverse relationship of factor, right? When I said 132 is 12 times 11, I would say, therefore, 11 and 12 are both factors of 132. They're not the only factors of 132. We also saw 2 times 66, and I guess it would be 3 times 22. No, 3 times 44. Right, we could take some time and list all the factors of 132. But we know 11 and 12 at least are factors because I've got 11 times a whole number to get 132. I've got 12 times a whole number to get 132, right? And it can be the same number. You could say 4 is a factor of 16. 4 times 4 equals 16, right? I have 4 times a whole number to get 16. It doesn't have to be 4 times a different whole number, right? So 4 is a factor of 16. But a multiple is the opposite relationship. We're saying 132 is a multiple of 12. $132 is a multiple of 12 because I can get 12 times something to get 132, right? So a multiple is a number that can be achieved by multiplying a given number by some other whole number, right? The difference between factor and multiple is which number are we starting with, right? If I start with 132, I can say 12 and 11 are both factors of 132. If I start with the number 12, then I can say 132 is a multiple of 12 because I did 12 times something to get that new number, right? 4 is a factor of 16, which means 16 is a multiple of 4, right? It's that kind of inverse relationship. It's similar to powers and roots, right? If 3 squared is 9, then the square root of 9 is 3. 3 times 4 is 12. So 3 is a factor of 12, and 12 is a multiple of 3, right? Back and forth that way. So 132 is a multiple of both 12 and 11. Right? We need to be very clear about those words because it's very common for people to get factor and multiple mixed up in their head. And having that mix up means that the other definitions that use those words really get mixed up. So maybe I'll post some other video. There are other videos out there that explain why this is the case. You don't need to understand it. It has to do with remainders and factoring and distributing. But there's a fair amount of symbolic algebra required to show that. So let's just show it with 528, right? That's the number we've been looking at. And we saw that 3 is one of the factors of 528. So how could we have seen that from the beginning? Well, here are my digits here. So I have 5 plus 2 plus 8. 8 plus 2 is 10. 10 plus 5 is 15. Do I recognize 15 as a multiple of 3? Yes, I do. So that checks. So 528 can be written as 3 times something. To get that something, I still need to do long division. But long division sucks, right? It takes time. It's easy to make mistakes. I want to do as little of this as possible. I only want to do it if I can be pretty sure that it will work, or if I've run out of all other options. Okay. So in this case, I am sure that it works. So switch colors here. 3 goes into 5 once. 3 times 7 is 21. And 3 goes into 18 6 times. So 3 times 176. Okay, that worked out. 3 was a factor, and there's that factor pair that multiplies to get 528. Maybe I want to take out another 3. Can I do that? Well, one way would be to long divide and see if I get a remainder. Hopefully not. But it'd be a lot faster to just say 176. Those digits are 1 and 7 and 6. Well, 6 plus 1 is 7. 7 and 7 is 14. Is 14 a multiple of 3? No. Well, when your sum is more than one digit, you can actually keep on going. You can take 14, 1 plus 4. If 14 is a multiple of 3, then this should still work. 1 plus 4 is 5. 5 is not a multiple of 3. As opposed to 15, if I add up those digits, 1 plus 5 gets me 6, and 6 is a multiple of 3. Right? So sometimes you're going to keep on using that rule a few times. Hopefully within one time you recognize, just depends on how well you know your 3 times tables. Okay? But 1 plus 7 plus 6 does not work out for me, so I'm not going to bother with 176 divided by 3. That's a complete waste of time. I'm not going to do this. But if I erase that instead of scratching it out, I recognize 6 that's even. Oops, that's not the, no one to push. Right, 6 is even, so I can jump to 2. But doing all of these 2's was a little tedious. I had a whole bunch of division. Notice once I got to 66, I could get 2 numbers that are a little closer together. That tends to be a little bit nicer. So instead of always taking out the smallest possible factor, sometimes it's nice to jump a little bit bigger. Unfortunately, 5 doesn't work. And it's not immediately obvious what else will work here. Now, if I'm trying for 11, 1 plus 6 is 7, which is my middle number there. So it's actually clear this early on that 11 would work. But if I tried to do 11 from the beginning, 5 plus 8, 8, 9, 10, 11, 12, 13. I can't get 13 as a middle digit, right? So that trick of the outside numbers adding up to the middle number fails once the sum of those outside digits is itself a 2-digit number, right? So I could start with 11, but why would you start with long division with 11 unless you were sure it would work, right? Here I'm sure it would work, so I am going to switch to that. 176 divided by 11. 11 goes into 17 once. 17 minus 11 is 6. Bring down this 6. 11 goes into 16 6 times. No remainder, right? So I have 11 times 16. And then this 3 is still there. Now, through this factoring process, it's an ugly 3. Through this factoring process, 11 and 3 are both prime now. If you have a factor that you've already memorized its own factorization, there's no need to do any more long division, right? If I know 16 is 4 times 4, I just write that. And then 4 is 2 times 2. And this 4 is 2 times 2. So there's my 4 2s and a 3 and an 11, right? 4 2s and a 3 and an 11. These numbers look very different than the other list of numbers. That's because I just use a different path to get there. And to get all the factors of 528, I would look at all the different combinations of 2 and 3, and 2 and 2 and 3, and 2 and 11, and 2 and 2 and 11, and 2 and 2 and 3 and 11, all the different ways we can arrange that. And that will give me the list of all factors. For right now, I was only interested in the prime factorization of 528. All right, so we've done a lot so far. We've looked at factors as a whole number that can be multiplied by another whole number to result in a given number. Right? If I'm starting with 12, I'm looking for numbers that can multiply to get me 12. And we've looked at multiples, a number that can be achieved by multiplying a given number by some other whole number. Multiples of 12, I'm doing 12 times something else to give me a multiple of 12, right? So multiples are always going to be bigger than that number or the number itself, right? The smallest multiple of 12 is just 12, or 12 times 2, 24, 36, 48, and so on. Factors, I'm looking for, well, what could I multiply to achieve 12? I could do 2 times 6, or 3 times 4, or 2 times 2 times 3. All of those are factors of 12, right? They're the largest possible factor, if you go back to here, is the number itself, right? 1 times that number. Otherwise, you'd end up having to use a fraction for your other number, right? So using whole numbers, the largest possible factor is the number itself. The smallest possible multiple is the number itself, and then you're going in opposite directions, either multiplying or dividing. Okay.